Okay, we are recording now. You're listening to this lecture for 4th, 6th, and 7th hours, but if you hear any noise, this is first hour. Okay? So as we go through and talk through the lecture, you will hear questions. If there is a question from the class, I'll try and reverbalize it so everyone can hear. Let's go ahead and get started with our bell work. What we want to start off with here is really just our work with box method. And we could go through and do the quadratic on this if we wanted to, but really the box method is the easiest for us. And if we factor this, we end up with 3x plus 2 and x plus 1. From here to solve, 3x plus 2 is equal to 0. And of course, x plus 1 is equal to 0. 3x is equal to negative 2, and x is equal to a negative 2/3. And x is equal to negative 1. Now, this is review for you. You've seen this with our factoring work. But I will tell you that in this next chapter, which is chapter 10, we are going to use this. We are going to see some places where we need to know how to factor. In fact, we'll see one of those problems today, and then we'll see the rest of them not next week, but the week after, when we start talking about lengths of segments. So, today we start into chapter 10. And chapter 10 is all about circles. Now, I should tell you a couple things about this chapter as we get started. First and foremost, circles are a very interesting part of geometry. And in fact, if we revisit the original Euclid's elements, he uses circles in a lot of very interesting ways. And really, to me anyway, approaches circles from a manner that I probably would not have if I was starting this off. The reality is circles hold a lot of, to use a not correct English term, specialness as far as the way that we can relate different lines to a circle. And the other thing that's interesting about circles is a lot of the properties and a lot of the things that we have already seen as far as like angle addition, segment addition, will now adjust to talk about arcs. So today's section is really just the beginning. Honestly, I don't expect to show you anything that you probably have not already seen. We're going to go through all the vocab for circles. We're going to talk about properties of tangents, and then that's about it. On Monday, we'll dive into work with chords, and from there on, we'll start talking about angles and arcs and how we can relate the two, and we'll get to a good place with circles. It is a very rich subject, but one that we really have to kind of pay attention to. All right, so that being said, let us go ahead and start with some definitions. Now, the first of these definitions is probably the most obvious, and that is of a circle. We define a circle as a set of all points in a plane that are equidistant from the center of the circle. So that means if I have some sort of circle, I can find a point on that circle, and the distance from that point to the edge is going to be the same in all directions. This seems kind of obvious to us, but it's one of those things we forget. We forget many times that I can draw a line from that center to the edge and have a consistent distance. And we'll see the implications of that as we move forward on Monday and Tuesday, because it allows us to subdivide a circle into different kinds of arcs. Now, that distance from the center to the edge we call the radius. Now, we kind of have to make a bit of a departure here from our normal MO. A lot of times we talk about a radius as a distance, but the reality is a radius is a segment. It's a piece of a line that goes from that point to the edge. And it's helpful for us to think about it in those terms, because if we can explain it in terms of a line, then all the rules that we have for linearity continue. we have to remove ourselves from this idea of distance. And it's an interesting part of the way that we teach mathematics and the way we explain mathematics and have historically explained it, because we like to use this idea of distance, but it has its limitations. Alright, so if we have a center, circle, and a radius, well, we now have a bunch of other definitions. We have a bunch of other definitions that we can do. The first is that of a chord. And a chord is a segment whose endpoints are on the circle. So, that just means that I have a line that goes from some edge to some edge. Now, I have an infinite number of chords that I can draw in this circle. I do have some specific ones, and that most specific one is a diameter. A diameter is a chord that contains the center. Now, again, we think of a diameter as some sort of distance, and a lot of times we'll talk about the diameter as the distance across a circle. But that's a fairly limiting idea. It's much better for us to think of this diameter as a chord that contains the center because, again, we can use our linearity, but more so, in this case, a diameter helps to subdivide that circle into two congruent arcs, which we would have as the top arc and then the bottom arc. We have a secant, and a secant is a line that intersects a circle in 2 points. Now, the key to a secant is that it goes through the circle. It doesn't start and stop on the edges. Later on, we'll define something called the chords of a secant, meaning that part of the secant that's inside the circle. But for our purposes now, we just need to remember that a secant is a line that starts on the outside and goes through it. Now, I say a line here. It could be a ray if we wanted to. Remembering that a ray starts at one point and continues on. If I had that ray start outside and go through it, I'd be good. And then last, I have a tangent. And a tangent is a line that intersects at exactly 1 point, which is what we call the point of tangency. Now, I like to think of the tangent line, instead of intersecting at exactly 1 point, a little bit easier for me, I think, is to think of a tangent line as resting against a circle. It's just barely touching. And that place where it barely touches is the point of tangency. Give you a second to get those in. You know, that's a good question as far as relating the tangent from trigonometric ratios to this tangent. And they are the same in that if you think about what the tangent ratio as the opposite over adjacent, which is the height over the distance, we can use that exact same thing when we start talking about the triangles that we're going to develop here in a bit. And we'll see that theorem today, actually, that development of the triangle. We actually use this idea of tangent in myriad other applications. All right, we're good? All right, so just to kind of give you an insight, I may give you a problem that looks like this. Identify all the parts of this circle. So, let's just go through and let's label some of these parts and let's list them out. So, a lot of times I think it's helpful for us to start with the specific points that we see. And the first is always the easiest, which is the center. And in this case, the center is point C. We have one other special point, which I forgot to label now that I'm noticing. So let's call that point J. And that is then the point of tangency. All right, so I've got that. Okay, who can tell me a chord that I have here? Sorry? A, E. Excellent, very good. So I have a chord at AE. And DG, excellent, very good. And we have two of them. Again, even though we're going to call this a diameter here in a second, it still is a chord. And so it's a perfectly good way to label that. And so diameter, we just said was DG as well. All right, how about a secant? Excellent, very good. So we have secant at DF, and then a tangent line. HF, excellent, very good. So, expect to be asked these questions. I expect on your test to be asked, okay, what is a point of tangency, which one is the chord, so on and so forth. The other place we use this, and you're kind of used to it, is I'll use this terminology in other problems. So I may say a line is drawn from the point of tangency J to a point on the diameter G. And you would have to draw that picture in. Now, you have to draw that picture in based on what I tell you. All right, very good. Okay, so those are our basic definitions. We have a couple other steps that we need to think through here. And the first is that idea of an intersection. All right? Now, if we think of intersections as a place where two lines meet, if we're talking about intersections of circles, we're talking about places where two circles meet, right? That kind of makes sense. The weird part about circles, though, is that there are three ways in which two circles can interact. We could have something like this, where we have 2 points of intersection. And that's obvious, right? We could have, though, 1 point of intersection. And if we have 1 point of intersection of circles, these things are called tangent circles, because there is one tangent line that we can draw that is tangent to all three of those circles. And the intersection point of those three is the point of tangency. And then we also could have no points of intersection. Now, it's obvious if I have two circles that exist out in space that are far apart from each other, of course they don't intersect. But I could also have circles that are nested. If we have a specific kind of nested circle where they share the same center, we call those concentric. So, you need to know the terminology of tangent circles and concentric circles. Concentric circles, a lot of times, if you think of the target symbol, that's a series of concentric circles. Second to finish that one. So, our work with Now, our work with intersections is important because it leads right into our work with finding lines of tangency. We'll get to a place where we're going to get to a place where I'm going to give you a bunch of circles and you're going to have to draw in the lines that are tangent to both. And there are certain properties that we can get from those tangent lines. And so let's talk about the different ways that we could draw what we call common tangents. So a common tangent is a line that is tangent, or a ray or a segment, that is tangent to two coplanar circles. Now, we obviously have to put in this idea of coplanar. It's kind of obvious at this point, but if we had skew circles, it would be really hard for us to have that common tangent. So if I have these two circles here, that would be a common tangent. The line that is tangent to both. And there are certain properties that I could determine based on that distance there and the distance then that goes between the two circles, right? If I were to think of some line being drawn between those two. Now, if I give you any two circles, you should be able to tell me the common tangents that exist between them. So let's go through our possible options. So if I gave you these two circles, I could draw 4 common tangents. So any two circles that don't intersect the 4 common tangents. If I have circles that are tangent circles, I can draw 3 common tangents. Of course, the one through the point of C at the intersection, and then the 2 that sit on the outside. I could have 1 common tangent. I have nested circles that do intersect. And then, of course, for concentric circles, I have no points of intersection, and so I have no common tangents. So, on your test, you will see a question. Okay, here are 2 circles. Draw in some common tangents and tell me how many there are. Now, the purpose behind this, again, there are properties that we can get out of this, but it also helps us to functionally get a grasp of how these circles interact. And we can start to see this come to fruition when we look at certain theorems. So, let's take a look at our first theorem. Theorem 10.1. In a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at an endpoint of the circle. All right, so this is a biconditional statement, goes both directions. If we have a circle then and a line tangent, we know that there's a right angle, and vice versa. So, let's take a look at what that means. I have a circle and a tangent line. If I draw a line from the center to the point of tangency, it will be a 90-degree angle. Now, you'll hear me say this a lot because we'll have some big circles that we need to dissect, and we'll have a radius and a tangent. And once we know that we have that 90-degree angle, well, we could draw in a right triangle. And we know that if we have a right triangle, we can do all sorts of other stuff with it, right? We can do our trigonometric ratios. We can use Pythagorean theorem. It's very helpful for us to be able to see this. This is how we can create those distances. Now, functionally, we'll see a couple problems using this at this point. Like I said, later on down the line, we'll use this to actually dissect larger circular systems, if you will. But let's work through a problem that we may see that relates to this. Good. All right. So let's say I gave you this problem, and I said, is line AB a tangent? Now, in order for line AB to be a tangent, I have to know that this is a 90-degree angle, right? Because it's a biconditional statement, our theorem was. So if this is a right triangle, then that's a 90-degree angle. So yes, in fact, AB would be a tangent. So if you remember from chapter 7, how do we prove that a triangle is a right triangle? We use the right triangle postulate, which we could expand to use what famous theorem?
The H word.
Nope.
Oh, well, I don't know.
What's the famous theorem we talked about in right triangles?
Pythagorean.
Pythagorean theorem, right? Pythagorean.
I don't know what.
So, what we want to do is test it out. We want to see, is 12 squared plus 5 squared, in fact, equal to 13 squared. So, remember the equal sign with the little question mark says, I'm going to test this out. I'm going to see if this is right. So, we have 144. Still are looking fours there. And 169. Still testing this out. But, in fact, I do see that that is correct. So, in order to answer this question, and in order for you to get points on a question like this on a test, you have to say yes. AB is a tangent. Alright, so for something like that, we're just going through, trying out Pythagorean theorem, making sure that it works. Now, let's say that I gave you a different style of problem. Same idea, but let's say instead of being given all the sides, I am actually having to solve for one. So let's take a look at something like that. Kind of weird. There it is. So, you would see a problem that's like this that says, what is the radius of this circle? Now, we do notice that we have a right angle right here. So we can use our Pythagorean theorem. But the key here is that this whole distance is the hypotenuse. So, r squared, which is that leg, plus 12 squared is equal to r plus 6 squared. And this is, of course, where we use our factor. So, r squared plus 144. And if I expand this out, remember if I have r plus 6, I have to do the box to expand it all out. This becomes r squared plus 12r plus 36. And then at this point I can just solve, right? If I take r squared from both sides, these cancel.
For that, you put both of those, like r squared and r plus 6 squared in the box.
Only the r plus 6 squared in the box. This one I can, because the squared is on this one and this one individually, I can just square those. But this one, the parentheses, I have to put into the box. Good question.
Look at it, 12R.
When I put it into the box, remember that if I do that, I have r squared, 6r, and then 36. Right? So then r squared plus 12r is 36. From here I can solve. I get 108 is equal to 12r, and then r is equal to 9. Now, it's important to remember that in this situation I had to use the box to expand it all out, but I didn't need to use the box to solve because the r squareds dropped out. Now, that's not always going to be the case, but it will end up being a lot of it. Good on that? Alright. Alright. We have one last theorem. This one's a much easier theorem to understand, especially. This theorem says that the tangent segments from a common external point are congruent. So, what this means is, if I have a circle and a tangent, and then I draw another line that is tangent to the same circle that starts at the same point, those two lines have to be congruent. Now, the proof of this, the original proof is this exact same one that I'm going to walk you through here. Okay? And you will need to know how to do some of these proofs. We're not going to formalize this one, I just want you to kind of think through it. Okay, if we start with that original line, and then draw in that other one, and then draw in our radii, and then a line from the endpoint here to this, we end up having two right triangles, right? Because we had a radius and a tangent, we know that that's a 90-degree angle. Well, if we think about what we know from triangle congruence, we have a 90-degree angle, so that means that we could use hypotenuse leg. The hypotenuse of this triangle is right here, and the same as that one. The 90 degrees, of course, are going to be the same, and then we have two radii, so those are going to be the same. So we can prove that this triangle and this triangle are congruent via hypotenuse leg. And if we can show that, then we know for sure that those two tangents are the same, because congruent triangles, congruent corresponding parts. I like to think of this theorem, and if you've ever opened up your car hood, seen all the belts. Now it's usually just one, maybe two belts. I think they call them the big one is a serpentine belt because it kind of wraps around through the car. But if you take a look at that, you'll see how that belt goes around those flywheels. And a lot of the sizing of those belts is based on this very simple premise. Now, of course, there's usually another flywheel at the end, and there's a little bit more that goes into it, something we'll see a little bit later. But at its core, this is really all we're doing. Now, you will see a solving problem with this, and at this point, again, we're just kind of getting used to this. We would just set these two equal, and then go from there. 17, 4x, x is equal to 17/4. Questions on these two theorems? Questions on any of the other terminology or anything that we've done? All right, then let me give you your homework. That is homework, and we are good to go. If you go back to that part.